Okay, so this week we are going more into post-tensioning construction, and we'll talk about some sequencing and some other details related to what we started last week, which is to do with post-tensioning or PT. Now, post or pre-stressing, as we know, they're both doing the same job in the end, but the sequence and methodology and the timing is kind of different between the pre-stressing or pre-tensioning or post-tensioning or post-stressing, right? Just for your information, the trend usually we call pre-stressing as what we do before, for precast systems, and post-tensioning for in situ constructions. Yeah. So these are basically some notes which I taken from drawings, and they can be different from one drawing to another. And you can still use in detailing the project assignment number 2, which we started talking about more during the workshop last week. And these notes will help you to, again, assign the required detailing for your cables. So if I go through them one by one now, as I've showed you before in week 1, when the first task, if you remember, when I asked you to look at notes in the first sheet of structural drawings, we talked about the angle of repose. If you remember, when I asked you which note will talk about safeguarding the neighbor's property or services. Now, if you got a post-tensioning system in your project, then definitely notes similar to those should be sitting there as well, right? So what I'm trying to say, these notes are not always in any engineering projects. They will be there only if there is obviously post-tensioning. So for your work as well, an assignment, and for your learning, these kind of notes should be understood carefully and also used as required. Now, I will go through them one by one as required. This one basically always reminds the construction engineer that whatever material they're going to supply should be in line with this condition. So this one talks to you about what concrete strength we need to have. Now, basically, this is to do with the contractors who are going to supply the concrete, or the contractors who are going to work on installing the cables, and they are saying to do with the local standards. And AS 3600 is the standard for concrete, regardless PT or RC. Yeah, we have the same code. Now, just an example, the local standard requests always our conduits that we will talk about. You remember the conduits for post-tensioning? They must be filled with concrete, unlike other places or other standards where they allow to have it. What I'm talking about is this. That was the document I was trying to search for. I'll share it with you. So this is kind of, let me go up. This is the conduit or the duct. This one here is the duct. As I said, we use the system when we have post-tensioning. So we're going to place the cables. Then after we place the cables, we're going to pour the concrete. Then after we pour the concrete, we're going to tension the strands. Now, what I'm trying to say is someone can imagine inside this conduit, we're only going to have loose cables, whether 4 or 5 or 6. And what I'm trying to say is after we tension the cables, let me see if we have a cross section. I'm just trying to go for another image. No, it's not there. So I just want to go to look at a cross section for those ducts. Maybe this one is helping. So that's what I'm trying to say. Those cables here, or the strands, they kind of originally going to be loose, and there is kind of, this is kind of a container. The duct, this aluminum material, it's going to be kind of a container. And locally, the AS, the standards I was referring to, it requires, if you're going to construct any post-tension systems locally, you have to fill or grout. After you tension the cables, after you tension them, you have to fill the conduit with concrete and grout. How we do this? We do it by this kind of tube. So this tube usually is provided to pressure in the grout after we finish and tension everything. Usually this tube will come out from the live end or dead end. So we will talk to you, by the way, this is the dead end, which I was always talking about, where we're going to have this kind of anchorage shape, which we call it onion end. And this is another dead end, right? So we'll talk about this more later. What my point here was, is I just want you to imagine, so this is a cross section for the conduit, and the cables maybe 3, maybe 4, maybe 5 here. Don't expect that we're going to leave the tube with air or void. No, locally we have to grout it, and that's where the standard would have to be followed. So that's one thing. The other thing, this note is talking about the maximum shrinkage strain, which is, this will be coming from the concreter who are going to supply you with the concrete. They need to know about these figures, so they will kind of ensure whatever shrinkage going to happen, drying shrinkage that will take place after they place the concrete, it will be within these kind of figures, 700 microns, which is the strain measure that will help. That's what the designers use. As I'm going to take you through these slides, when the designer have designed those cables, there are a number of losses. Losses can be temporary, can be permanent. One of the losses that will happen in the cables are due to shrinkage, because when the concrete shrinks, it will, even after you tension the cables and put it under stress, compressive stress, shrinkage can happen. And shrinkage may happen in a way where the direction of reducing the concrete size will be in the same direction of compressing. What that will do will loosen the cable. And when the cables get loosened, it means for us losses in the stresses. So the engineers will allow to recover those losses, right? That's why we need to be careful, and the engineers, and they will need to specify for you what they allowed for. Eventually on site, that's what we're going to order. Again, the engineers will calculate losses. One of those losses types are related to shrinkage. When the concrete shrinks, it will reduce its size, as we discussed before in a different topic. When I'm talking here about size, I'm talking about fraction of millimeters. But this means, and eventually, you're going to loosen the tension. Didn't we say we're going to tension the cables, then we're going to apply compression to the concrete? Now, imagine the concrete after a few days from fully stressing the slab going to get shrunk. So its size going to reduce by fraction of millimeters or few millimeters, very few, 2, 3. What this will do, it will loosen the cable. So it's actually losses. And the engineers will allow for those losses by this figure. So that's just for you to understand why these are required to be followed when you order a concrete and make sure it's going to be placed in such arrangement. Same thing with the steel. You know, steel, it's like rubber. If you tension it, with time, it will get loosened. It will get looser and will get what we call it relaxation. The cable will get relaxed. And this is also will be allowed for in the calculations by the engineers. So what they allow for is what is specified in another standards related to stress relief. So again, now basically these kind of notes, PT1 and PT2, should be confirmed by the suppliers who are going to be ordering and supplying you with such material. So in other words, the material that you're going to get from several PT companies around, they will have those certificates confirming to your project that they will have these kind of relaxation, stress relief values, because the engineers has allowed for such values, right? So also the maximum breaking load. So the 12.7 diameter cables or strands will go 184. Right? Can someone calculate for me what's the stress, just for your understanding? Can someone just, this is a force, breaking force, and this is a diameter. So basically find the area of this strand and divide this force, change it to Newton, sorry. So change this to Newton and divide it over the area. Can someone just let us know what's the MPa going to be there? Just so we can feel the numbers. Yeah, it's taking that much. Any values there? Anyone got access to calculator? Nowadays it's available anyway, those calculators. Yeah, so that's the diameter we have there. This is the radius. Yeah, this is the area. And divide this, I will just multiply it by 184,000. Just changing this to a Newton. See how much it is. 1,000, about 1,500, 1,400 MPa. Can someone tell me what's the usual steel value that take for MPa? This is the breaking load. So still we have safety factors there to bring it down. It's going to be about 1,000 MPa. Okay. So what was the steel? Any idea about the normal steel that we use in concrete? How many MPAs it can take, or what the engineer should allow for? Just for your experience. So no idea. It's 500 MPa. So normal steel that we use in building, and for reinforced concrete, they take only up to. They are manufactured to take only 500 MPa. But you can see now the cables got much higher grades. Those strands that we use in post-tensioning, they can go up to a breaking load. It can take you up to 1,400. And this is without safety factors. There should be safety factors which will bring it down, say, to 1,000. So yes, they take much more higher. They are more expensive eventually, but they're not in the slab. Eventually, they're not as many as the steel bars with 500 MPa. All right. So again, the notes here will kind of standardize what the construction sites should use, and to make sure everything is in order. Note number 3, it is talking about the ducts, which I showed you in this. We're talking here about, again, the engineer want to tell the builder what did he or she used in their design. So to make sure, because those ducts eventually, for example, they got particular friction. Now, I talked to you about losses already due to shrinkage. Also, there is another type of shrinkage, losses, which is happening due to friction. As we have cables inside the ducts, and as you try to tension it, then release the load, there's going to be some sort of friction between the duct and the cables. Those friction will got an impact on the lost forces, because when you have friction, that means you're losing forces. So each duct type got its own friction coefficient. And again, that's an example. Why do we all need to use this, the specified product, and why the engineers are specifying it for us? So the ducts as well here, it is specified for us to use. We have the flat duct, which is this one. The one I was just showing you in this document. Like, this is a flat duct, and it's got different sizes. Some of them will fit 3, some of them will fit 6. And the drawings will be talking about them here. All right. Say this is the note I was talking about, PT4. All ducts shall be pressure grouted after completion of stressing and the live load anchorage recess made good with stiff hard ground mortar. So this is just the patching that I was talking about last week, and also we'll talk about this week. So the live end needs to be patched, whether the pad is from the top of the slab or from the side of the slab, needs to be patched. That's one thing. And before that, after you finish the stressing at different stages, we need to apply grout. This is all in accordance with this standard 3600, right? So these, again, notes we need to be aware about. You need to consider that it's something different than normal concrete system. Note number 5 here, it's really talking about the sequencing, how the tensioning is happening. The tensioning does not happen in the next day. So when you pour the concrete, you wait, when you pour, so as I said, in terms of steps, first thing, you're gonna pour up your tables, your formwork, then you're gonna place the minor normal reinforcement. And let me just see if there are some, no, I don't have any drawings, but from if you remember last week, I showed you some setup for PT the slab. So again, step number 1, you will be placing your formwork. You will be placing the minimum bottom reinforcement you may most likely have. So there's always minimum reinforcement that will help the designers to control shrinkage, right? There are sometimes minimum, maybe 4 bars only, maybe the metal deck. Sorry? Is there a question, MB? Yeah, anyway. So after you place your cables, you're going to be pouring and place all the required additional reinforcement, which should be minimum. You will be pouring the concrete. And after you pour the concrete, until now, nothing is stressed. After 24 hours, which is 1 day approximately, the contractors will come and stress only 25% of the stress force, total stress force. So stress force is not the 184. It depends on the safety factors the engineers used, and that will be specified by the engineers, right? So it's going to be 25%. Say it's going to be up to about 300 MPa or 250 MPa, right? So that's what you do after 1 day. So all strands within a cable, what we mean all strands, we're talking about these ones. So this is 1 strand. So here we got 4 strands. So all of them should be stressed to this figure we're talking about. 25% of their final load. The braking force is a bit higher. So the braking force for 12.7 strand, it is 184. But their safety factor, typically we should take it down, say for maybe 150. And then they need to reach 25% of that 150. Now, then step number B, 100% of stressing should be applied at minimum concrete strength. Once the concrete reaches 25 MPa, who will tell you that? The reports coming from the concrete supplier. They will send you, maybe after 1 week, they will say your concrete already passed 25 MPa. Then your PT contractor will come and get your cables fully stressed. So in other words, it's 2-stage. Sometimes we can go to 3 stages. It's up to how large is your sections. It's again up to the design. The designers with their softwares, they can specify whether 2 steps or 3 steps, but ideally or typically 80% of what people work with, or more, maybe 85%, they go through 2-stage stressing. 25%, then 100%, right? To make sure the stresses are evenly distributed inside the slab. Remember, all what we're talking about so far, it is post-tensioning. It's nothing to do with pre-stressing, which we talked about. Pre-stressing was different. Pre-stressing, we will fully stress the cables to whatever they can take, then pour the concrete around it, which is what we had with the hollow core systems, etc. Okay, here what we're talking about is post-stressing or post-tensioning. There is a third note here about stressing. All slabs should be stressed before stressing the beam. This is something you need to think about with your project as well. So if the question is asking you to talk about stressing sequence, so again, as what we found in your first submission, students miss doing the job, not misunderstanding what to do. They kind of bypass requests made to you in the assessment. And I'm kind of, most likely your assignment 2 did ask you to talk about the stressing sequence. And I see in the past students miss those things. They just don't write. They show me some drawings and that's it. They don't talk about what they're supposed to learn from this slide and report it on their drawings. So I need to say on your drawings, you need to, when we come to talking about slabs, you need to understand that stressing the slab should be done before stressing the beams, because the slabs are actually supported on the beams. Again, some people will ask, why is this happening? Because the stressing process will cause some additional external reactions. When you stress a slab or a member, they will result in external reactions, which needs to be carried by something outside. So we need to make sure the slabs, which are supported by the band beams, are fully stressed. Then when this is done, we go and stress the beam to make sure it's going to carry what's supposed to be eventually carrying, right? So that's basically the reasoning why all slabs needs to be stressed before stressing the beams. You cannot stress the beams and then apply the external load on it, because the beams are supporting the slabs. All right, so this is to do with the stressing sequence, very simple. So far, you had 2 steps to 2 stages that will let you stress your slab with. As I said to you, there are cases where the engineers may want you to kind of stress your slab over 3 stages. I think maximum that would happen 3. When you have large beams, like the beam can be as deep as 1.5 meters, right? Very deep beam. You don't want to stress it in a rapid sequence. You want to stress it more gently. So we do it at 3 stages. Maybe you will have one at 70% or 65%, and then you go up to 100% in the third one. But this is, again, that's what the drawing is going to say. It's not, it's not changed over side by side, because that's what the engineers calculated. So the last note here is really going to help you to determine the figures. And that's, again, something you need to document in your assignment. This will tell you about the type of ends we have in the cables. We have live end anchorage. Live end, that's where we call it live because that's from where we're going to stress the cables. And an example of this is just sitting here for you. This is basically a live end, right? And this is basically is what we have from the side of the slab. You remember I talked to you last week, sometimes the best way that for the engineers is to place the live end at the side of the concrete slab. So if I can go back, let me go back to my sheet here. When I say the side, this is maybe your, just to clarify again, this is your slab. And ideally we have our cables coming with a parabolic shape like this. So I should not go to the very end. I should just start here, and for my dead end, it will stop here. So usually the dead end got this onion shape. This is the dead end, DE. And I'm saying here on the left, it's the life end. It's ideally or the most efficient design when you put your life end on the side of the slab. So this figure, it means it is life end anchorage, which is shown by that. Sometimes we're not able to do so. So we're going to use a tray or a pan. And what does that mean? It means your cable is actually starting from the top of the slab. And we show it something like this, right? And we show the cable just coming from. So this means the contractors are only able to stress it from the top. Sorry, I'm trying to throw a person here who will be stressing the cables from the top. Sometimes you already have a building here, you can't do it. Sometimes that's the boundary line. You cannot put even some scaffolds to stress it out. Yeah, but as a large project, if you're always going to be stressing from the top, that will cost more because your cable is going to need to be more in terms of number. Maybe you're going to end up requiring 5 strands rather than 4. In other words, if you're going to use the orange profile, you may require only 4 strands of those in your, so 1, 2, 3, 4. However, in a larger project, in a project where you are not able to stress it from the side, you're only able to stress it from the top, that will weaken the cables. And what does that mean? You need to put more strands, which is 5. And that's what the engineer is going to say during the design process. Now, coming back to this image, someone will ask, what's this? This is a very, it's kind solid end. It's going to be staying in the slab typically. And that's how, now just to zoom in, this one will allow for the grout tube, which, as I said to you before, this is locally a must happen because it will pressure the grout. Remember one of the notes I mentioned to you here? We have to, this one, number 4, duct should be pressured, grout after, yeah? That's how we place the grout. We place it through this tube, and usually those ends will got this facility. Now, one of the other features here we will talk about later is the wedges grips. These grips, there's got some mechanism where to allow you to pull the cable outside. But when so what we do, we pull the cable to this breaking to the 25% or 100%. Then once we release the load, these grips will prevent the cables from slipping inside. Now, as I said to you last week, those grips got different qualities. Some of them will allow for 6 millimeters slip. Some of them will allow for 4. Those 4 or 5, they got a very large impact on losses. So another type, I've already talked to you about 2 types of losses, one of them due to shrinkage, one of them due to friction between the cables and the duct. And now the slip that we can have between the cables and the grips, those may be 4 millimeters, 5 millimeters, that will cause also losses because as the cable slips, it will get relaxed. And that means you're going to reduce the forces we need to put on the concrete. So that's what we have at the life end. The life end, in summary, it is the end where we can stress the cables, where we got the wedges to block the cables from slipping and going back into the conduit. We got this grouting mechanism and tubes placed, right? Now, someone will ask, what's this? This is just to allow, you know, as we said, everything gonna be loose. All those cables gonna be loose before you pour the concrete. To allow for the opening from the side, you know, of the slab, to allow for the opening, we use this. Let me see if I can find for you a real image. I will show you. Maybe, yeah, this one we can only found it from. So I think here I'm seeing something here. I'll share it with you just to let you. If you have any questions, please come in, stop me, and I can explain it. But I'm just trying to find an image to show you where is this plastic is used. Yes, I'm seeing many types, but I want to show you the local type as well. Yeah, I think these are helping. Yeah, so what you can see here, you see this is the black tube. It will just allow for the, because here we got the formwork. I was talking to you before that the live end, it's used when we want to stress the cables from the side of the slab, right? The orange option. So how it's actually installed on site, it's installed like this, and you can see the black plastic. It will allow for the void. It will allow for the void again here, this one. It will allow for the void, and the void eventually, which is talking about this one here. I just want to see how. Here we go. This is a very good picture. So yeah, it's simply to allow for this void to be formed. So before we pour the concrete, we have to place the black, or in this image, it is actually white, the black plastic that will allow for this void to take place after pouring the concrete, which is just a void that will allow you to do the stressing business for your strands. Here we got 4 strands, and that's really what's happening. So this picture really, it is what's happening for yeah, I think I'm just trying to say there are very good examples in this side. Yeah, but again, these may be international. I think this is an international project, but basically the pockets, they look like this. And later on, after you're done with stressing, we will patch those voids. Okay, but let me go back to my notes. And I was talking about the types. Now the pan, yeah, so yeah, the first one I was talking about, it is the live end anchorage, and this means it is the side. This second image, the second detail here is the dead end, and the dead end basically it can come up with different forms. What's locally basically used, here we go. This is 2 dead ends, which is mostly used locally. This one, it is an onion shaped dead end, which is the side that we basically don't stress from. It is just the side that we keep, which is this one in my image that I shared with you. So this is it is the end where we don't apply stresses from. Right? What else? This type here, it is just they use a piece of plate. Now, the designers will decide whether they go with the top type or the lower type. Right? It depends on how much anchorage. Again, as we calculate losses, it will depend on which type you're using. Sometimes this is enough for the loading type we have. Sometimes we need more because the loading and spans, they are larger. So we want to prevent that slippage to happen. So we end up using this more expensive dead end that got special plating business. So the anchorage will be higher, and that means the slippage in the cables will be less. So that will help you to have better stresses. But it's not, usually this is used in slabs because we don't need that high. Now, can I ask you guys, hopefully you are all active with me there, why the tube's coming out from here? Why do you think the tube we said it is here, and that's how we're gonna pump the concrete. Can someone tell me why do we have the tube coming out from this end as well? Yes, it is the dead end, but for excess of what? So remember why we're using the tubes. We are using it to fill the grout in the conduit, for the void to come out, or maybe trying to say for the void to be filled with grout. I'm not sure if that's what you're trying to say, but usually those tubes, they will help the contractors to find out that yes, the grout is getting. Now this tube is kind of, as they fill it, it will confirm that there is adequate pressure happening. Because as per the notes, because they're going to be measuring the pressure of concrete we have. And this tube, from one end, they're going to pressure the concrete, and the other end, they're going to measure the pressure of the concrete they pressured. Because if you remember the notes here, they are talking about pressured grout. Pressured grout. So you don't just fill the grout, they will be putting it under pressure. They got slots in the tube. One of the ways they do it is they got slots in the tube, and the tube will be filling the gaps around within the conduit and around the cables. And the pressure, as the pressure increases very high, that means it's full. So they measure the pressure from this side. If they find the pressure is getting really high, that means the tube is full. It's already filled with grout. Right, so they do have the tube sticking out from both sides because it will give them an indication about the pressure. One side, they're going to pump in pressured grout. The other side, they're going to measure the pressure. And once the pressure leveled up, very high level, that means it's the void is already filled with grout. So as a key of inspection, this is just another. Someone will ask me, what's this? This is kind of a strange. Is this dead end or live end? This is a couple. And I think one of your examples here in the notes, the next one. So we talked about, I think I didn't show you this. Let me show you this as well. We do have it in our this document. Before I talk about this, let me talk about the pan. Here we go. This is a very clear example for a pan. This is where we have to stress the slab from the top, right? As I said to you before, these pans, they're going to happen on a frequent basis. So they're happening, it depends on the design. The slab you're going to design, if you can see, you're going to say, I want cable every 1.5 meters, which if this was, for example, a warehouse where the architect wanted fresh concrete as a finish, they may not like it. But again, sometimes you're stuck with it. So maybe they will decide to cover the whole slab with a vinyl or any other polymer material or carpet. Depends on what you're having, if it was an office, whatever. Okay, so these are the pockets. This is again a live end where we stress the cables or the strands, and then they will get grouted. The pan is again a piece of plastic you're going to be placing in your slab prior to pouring the concrete. Again, these details talking about the other pan for the end, life end, but this is the top life end. All right, a pan is another piece of, which looks here, it's a piece of plastic that will create this pocket on the top of your slab. Right, so, and what I talked to you about here was basically this type, this one here. All right, now, then the last one, the coupled anchorage. Sometimes we have slabs which are running for very, very long spans. Say you got concrete slabs, like for example, in a shopping center, the slabs can run up to 40, 50 meters long. And in this case, you will need to use couples. In this case, you will need to use couples, and couples can be something similar to what we have here, right? So you don't need a dead end here. You need to couple it up. So basically, in the end, there's going to be one. They're going to end up being one cable continuously running from one side to another. So if you need to use a couple, you have to use this arrangement where your cables here going to be matched with the cables on the other side, and then it's going to be a continued joint. That's where you couple it. This is again something the engineers will be deciding on. And sometimes if you don't want to have a life end in the middle of your slab because it does not look nice, maybe architecturally you're going to be requested to use these kind of connections because you don't want your cables to stop. If you stop a cable and you need to stress them, maybe you're going to need to make those pockets we talked about here. And sometimes you don't like to have these pockets in the middle of the slab, so you will use couples, and then you're going to take it to the far end, to the end of your building. So again, these decisions will be made during the design phase. Okay, so some other notes. That's note number 6. Let me just delete what we had there. Note number 6 was talking about the type available. So yes, these notes will be useful for you to use in your assignment. Yeah, so here they're just talking about the quality with this note here. They're talking about the quality sewage end. Usually sewage end is high quality material that can prevent all the rust. Yeah, because they need to stay for long term. You know, same as sewage pipes when they don't have adequate cover. Sewage pipes, talking about sewage pipes, they typically got special grade, which should be durable for 30 years or even more, 50 years or whatever, because they're going to stay forever. So what we're talking about, the material of all the ends, like these, the qualities of these ends and the couples, all these ends, they have to have a sewage quality, which means they have strong resistance to rust and very high durability. The last note here, it is talking about the stage of construction, which you can see they are really simple, which I talked to you about last week as well. You're going to put the tendons prior to placing the concrete. That's basically the idea of post-tensioning. Prior to stressing, prior to cutting. So that's again the inspections the engineer should be doing. That's when you need to call the engineer who designed the project to come and have a look to what's happening. They need to come before placing the tendons to make sure whatever additional reinforcement, the levels of your concrete, the thicknesses of the concrete, it will help to verify the thicknesses. You cannot put the cables and the steel then ask for the inspection to happen. So to make sure that the thicknesses of the slab, for example, the 240 thick slab, the 450 deep band beam, the engineer should come and look at the formwork to check the thicknesses of the slabs are okay. Then before stressing the cables, that's after you pour the concrete, they should come prior cutting the grout and grouting to make sure that all strands are stressed, and you will provide the stressing reports as well. Okay. that's how the engineers will actually evaluate whether you have reached the required stresses is by looking at the extensions. So that's how the engineers evaluate, or you as well as construction engineers or site supervisors, how to evaluate that you have reached this pressure. Breaking load, we said we have, maybe we're gonna reach with the safety factor, we're gonna reach 150. Yeah, how we're gonna evaluate this is by looking to the extensions, by determining how many millimeters the cables have been actually extended outside. So if it was extended 5 millimeters, we convert that to stresses and we know how many kilonewton that was. Right? So I think we spent reasonable time talking about one page here, which I like to go slowly through that because some of those are many kind of those information should be understood carefully and applied, whether in your second assignment or used in the final exam. All right, the rest really, most of the rest of the slides we have today, they are images, which I've already shared with you over the other document, which I will add. So the other document I have, I will add it to your reading list. It's just a new document I found. So reading list for week 5. We had more generic, the PT drawings I shared with you, and more generic detailing. I will add this document for your information as well, if you like to learn from. Right? Just back to my slide. So yeah, just carefully go through these notes and see how you can apply them in your second assignment, or maybe you will have some questions related to them in your final exam. Is there any question about what I've gone through?
Yes, I have one question.
Yeah.
When we start today in the morning, in the first beginning, you said that we are placing the cabling for the post tension only. The cables, when we use the cable, it is just only for the post tension. That's mean it's not for the pre tension.
That's right. Yeah. So.
Oh, right.
No. The cable. So what you?
The cables, just the cable system. Let's say, not the
pre-stressing. So you're kind of like asking. In the pre-stressing, we also have cables.
Okay.
But the cables are placed before are stressed before pouring the concrete. Let me show you last week's lectures, which should be here. So week 7. So both systems got cables. We have to agree about this. This system here is talking about pre-tensioning or pre-stressing.
Yes.
Same thing. Now, yes, you can see there are cables, but the key difference here, there is no conduit.
All right.
And there's no conduit. And what's happening here? Here, the cables are stressed before pouring the concrete.
Yes.
Today, we're most talking about post-tensioning, where the cable's going to be placed and not stressed again until we pour the concrete and start stressing the cables. Tell me, what's confusing?
That's mean on the pre-tensioned, we are using the cable without conduits.
That's one of the differences.
All right.
Yeah, that's one of them. And
all
we
right.
are also one of the other things we said, we will be tensioning the cables before pouring the concrete.
Yes.
One of the special features about this pre-stressing, the cable is in direct contact with the concrete. Each strand, so this is a 12.7 strand here, yeah?
Yes.
Each strand is in direct contact with the gray concrete around.
All right.
Unlike post-tensioning. Post-tensioning, so what does that mean?
Covered.
That means it's covered, it's housed inside a duct or a conduit.
Yes.
What I want you to know, like engineering-wise, what does that mean? When you have the pre-stressing or pre-tensioning, or this example here, that means the way we transfer stresses from the strands to the concrete, it's happening along the entire contact length from this end to the other end. So there is a direct contact between the strand and the concrete. That means as we start from this cable, we will start transferring the stress, and it will keep transferring as you go inside the beam. Unlike this system here, post, which we're talking about today, the force will be actually applied from the end only, from the dead end and live end,
Yes.
when we have post tensioning, because there is physically no direct contact between the cables and the gray concrete.
Mhm.
So the forces, if we have, if I quickly draw another span, this is our span. As what I was trying to say, for the post tensioning this type, the forces will be applied from the ends.
Yes.
Because we have the dead end or live end here and there, which are the main features that will transfer the stresses from cables to the concrete.
Yes.
Unlike this one, so this is, I'm just here want to clarify to you the differences. Unlike this system, in this system, if this was our beam or slab, then we have the strands here, remember, are typically flat.
Yes.
Mechanically, we can't have them profiled, as we discussed.
Yeah.
And the forces we have applied here, they not only applied at the ends,
All along
they are applied over the entire length evenly, because there is friction. That's why, if you think about it, I will come to this point. You're gonna see in our today's topic here, we're gonna talk about this later. We always gonna have additional reinforcement here. We call it the edge reinforcement. You're gonna see this only when we have post tensioning, because we have a lot of concentrated force at the end, whether live end and dead end. Same thing with the dead end. Nobody asked me, why do we have, we will see later on details where we have additional reinforcement around the dead end as well, because we have very high concentrated force at the dead end, same as live end. Unlike the pre-stressing, we don't have those cages at the ends, because the forces are transferred not at one point over the entire length. So that can be another justification about why we don't have anchorage here, right? So let me go back. Did I answer your question?
Yes, thank you.
Yeah, all good. Yeah, okay. So any other questions? Right. So the coming slides, it's just that's why I was searching in the morning. I was searching for this document, which I will upload to you to scan through and learn from it and see, the coding that we do as well. Most of your slides really were taken from that document I showed you, VSL. VSL is just one of the brands that really the VSL. One of the VSL, it's one of the brands that they manufacture the PT components. And usually those guys here, they got also construction engineers, they got structure engineers, they can do design, they can do construction. This company can do the construction work as well as the design. Sometimes they only, as well as providing the material, right? So they can't do everything. Sometimes they only do the construction, depends on the project and what's going on there. So I've already gone through all those detailing for you, which talks about different kind of, this is again the dead end, which you can also view and learn from the other document I will share with you. This is just a plan view, looking at it from the top. This is just the side view, looking at it from the side. This is just the chair, which will confirm the heights that we talked about last week. So you remember when I showed you the drawing, the project drawing I showed you and talked to you about last week? It is to do with post tensioning. Usually pre-stressing, they come flat. The cables come flat, right? They don't come with a profile, with a parabolic shape profile. Why it's parabolic? Because they are mimicking the bending moment diagram, right? The cables are, when the post-tension cables, they are usually placed in a parabolic shape because they are mimicking or kind of simulating or reflecting the bending moment diagram. This is the live end, which I showed you with pictures. This is a plan view, and this is a side view. And there are different numbers. I know these pictures are not helpful. I will show you other pictures I got later on. Right? I will show you other pictures. This is just another. We talked about all those kind of things. The dead ends, just some details about it, cast into the concrete. As we discussed, they are just embedded in the concrete. They have the two famous shapes, the onion end and the switch end. This one got much higher capacity. It's more expensive. Free strand. That's what we usually keep the strands approximately 800 millimeters, just to make sure that this will allow for the grout tube to come out. So usually there's a free end. That's what I'm trying to say. There's a free end here, so the conduit will not stay all the way to the end. We have about 600 millimeters, so it will allow for the strands to be separated and distributed to get the concrete around it and achieve the bond with the concrete as much as required. The spacer plate, this one here, we've got spacer plate. That's for the onion, for the onion dead end. This is not structural. So that's just to help separate the strands. But you can see it's very thin, it's not structural, it's just to separate them from each other. It's unlike what we have with this type of dead end. It's quite thick plate and it is an anchor plate. So it says here for you the spacer plate. Spacer plate is just to space out the strands for the onion type end. So the onion type end, just to clarify, it is this one, and the switch type with a plate, it is this one here. And it's got different capacities, and up to the design engineer which one they want to use to give you whatever capacity and performance for your cables. Some detailing, all those really, yes, we have tables, which helps the design engineers to pick and choose. And it will be easy for the construction engineer to order for the project. So here we're talking about the switch type, which is with a plate, just a plan view what I showed you here. So basically what we're seeing here, it's re-shown here for you with a plan view. And number C, as I discussed, it is typically the free end 600 to allow for the spacing to happen between the cables. As we said, this is not structural plate, it's just to help with spacing the cables. In the market, they got the 12.7. We use this majorly for slabs, they are enough. And the 15.2, if your slab is really thick or carrying a lot of heavy loads, like heavy traffic load for bridges, you may be experiencing this higher diameter strands. Okay. So yeah, these kind of dimensions just to help. It's from the supplier like VCL or other products. They give you some dimensions just to help the construction engineers and the design engineers to correctly detail the ends and understand and visualize or imagine what kind of spaces they want in the ends. Right, so don't think these are design tables. We don't use this to design and say how many cables we want. It's just to give you an idea about the geometry, the size of the cables, and the size of the space you need at the ends. That's basically what they do here. Live ends, which I talked to you about. Live end, I think all of you know the features we have here. We have the ducts, the conduits. You know the business of the grouted tube. This is the sewage class or the sewage quality anchor head, they call it anchor head, which allows for having the wedgers. The wedgers, they are scaled up here for you. You see this one scaled up. It's one of the, as I said, these wedgers, they will stop the cables or the strands from slipping in the back in the conduit after stressing it. The level of stress we're talking about are very high. As I said, it can reach 150 kilonewton as per the first page we talked about. 150, it's a lot, 150 kilonewtons, right? That's each cable, each one. So to make sure after you take away the load or after you cut it, we need to make sure the wedges gonna lock it in. And whether you like it or not, there's gonna be some few millimeters of slip that will happen. The number of millimeters got high impact on losses. Losses means we kind of wasting steel. And if you use high quality wedge, that means the slip will be minimum, maybe 4 millimeters. If your wedge was bad quality, it can go up to 8 millimeters, which means that will cost you a lot. I will show you a curve to let you imagine what I mean, a lot and less. You're gonna see, as you're gonna see soon with some figures, graphs, usually the losses are happening during construction more than after construction. Because during construction, that's where you're gonna be pulling the cable and the cable will be moving few millimeters. That movement will result in friction between the strands and the ducts. So you're gonna have this loss. The wedges, things gonna slip here. You're gonna have this loss, and they are a big component of that losses. I will show you a graph. The early shrinkage in concrete, you know, shrinkage is gonna happen within the first 24 hours. So that's what I would say, and we're gonna be stressing during those hours as well. So that's what I was saying. Stressing will happen at the early stage, and loss is going to happen at the early stage. And you all know this is just a permanent formwork. It's just a plastic recess former to create that void I showed you before. Right. So that's basically what we have at the whether life end or dead end, which typically engineers inspect to make sure what's happening on site is correct. We need to make sure the dead end and life end are placed correctly. We need to make sure the draping are placed correctly. We need to make sure the number of strands are correctly used as well, right? Then again, this is just a plan view for the life end, which I will share with you the original document, which is this one here. I will share with you if you like to have it in your library. One other thing I wanted, I think, yeah, it's all clear. So as I said, these tables, they're not a design table. They don't tell you capacities. They just tell you the space we need to allow for. So the contractors or construction engineers, they know what kind of space they have. And usually these things are spaced out adequately. They're not really next to each other like cables. So A, for example, here, it will require you to have about 260 millimeter space. So that will help you to decide on the band beam. You know, if you've got 1.2 band beam width, you need to have an idea about what's going on here. You can't have 6 cables in 1.2 wide band beam. You can't have 6 because each one at its life end requires 265. Right? You can't have 6 conduits or cables. Right? You can't have 6 ducts or conduits or cables because each one will require about 2.5. If 6 of them, you're always going to be without cover. Okay, so it helps, these kind of tables helps you to construct the cable more than designing it. Now here we're talking, the slide is talking about properties to do with the strand. As we said, ideally in the local construction exercise, we have 2 famous diameters, 12.7, the smallest, 15.2, it's the next level up. Most of your structures are with this, they are enough for like residential applications. and office buildings. 12.7 diameter cables are adequate. And the area of steel, this is just talks about some the properties of the cable, which the engineers uses. So as I said to you here, we can reach up to the elastic modulus. Yeah, you all know for the steel is 200,000. So for this can be arranged. And that's what the design engineer uses to do their calculations. So, okay, the relaxation, as I said to you, there are losses that will happen after 1,000 hours at 0.7 breaking load. So that's what the engineers allows for. The losses or relax, when the cables get relaxed, which is permanent deformation, it means losses in the stresses, losses in the capacity of the beam. The engineers will allow for such things. Remember, this is not a huge value, so we're talking here about losing maybe 1 or 2 or 1 point or 3 point millimeters in a big span. It means nothing, but it just the engineers need to allow for it. Make sure they're gonna reach adequate levels. The elongations, right? The minimum elongations, like how many millimeters. For every 600 millimeter of length in your cable, the maximum we can allow for is 3.5%. So if you got that's what the contractors really carefully monitor as they stress. There can be a lot of risk of injuries especially with contractors. So again, builders or construction engineers need to make sure people who they're going to hire on their site, they don't want to have accidents because that will slow them again. Even if they have subcontractors, they need to make sure whoever is on site are experienced and done this many times and got all the safety measures with them. So this is really important for construction. It will give an idea for the contractor when the cables will get cut. There's a lot of incidents where contractors gonna overstress because missing a number, misunderstanding, something went wrong. And sometimes when they overstress a cable, it may snap, and it may snap a finger or cut a finger or get them really. There's a lot of, there are situations that can even break things around. Yeah, so to make sure they are always within correct safety measures, the manufacturer here is telling us that don't elongate 600 length of your cable more than 3.5%. So if you simply how this is measured, just a 3.5%, 3.5 divided over 100 multiplied by 600, that means 21 mil. 21 mil. So 600 millimeters. So if you got a cable, let's say you've got a cable which is, so remember 21 millimeters for 600 millimeter length, right? So if you got say 10,000, right? This 10 long meter cable divided over 600. That means 16 multiplied by the 23. So it is, yeah, it's reasonable. Yeah, it's about 380 millimeters. So in other words, if you've got 10 meters long cable, you are stressing, they need to know that they should not go more than 380 millimeter extension. As they stress and tension, they should know that they should never go more than 380 millimeters in terms of pulling extension, because that means they will start breaking the cable. Maybe the tool they're using to measure the stresses are not accurate. So that's where this kind of gives more warning and idea about what limits they have. All right, so now this table here, as I said, it's got some properties related to cables, and some of them are directly related to the design engineer, like what we have here. This is again to do with the proof load. The standard typically or actually request the manufacturer to check the load we're taking, and the proof is typically happen at 0.2% offset from the breaking load, right? So 20% 0.2% down from the maximum. So this is just a proof that the manufacturer is trying to say that our product is in line with the standard. So we are able to use it. That's basically a certificate from the supplier. Right. So again, this is to do with the material properties and how much they can take load and limitations on their performance. The tables below here is to do with the, we're still talking here about the number of strands and the coding for the tendons, right? So we've got different types here. So usually the strand 12.7, it's coded like this. And the last number here means how many strands we got. If we got 1 strand in the system, we can get this much, 2 by 2, 3, etc., etc. So these numbers is just represents how many cables we got in our setup. Let me show you here. This is it here. So this means we got four strands. Sometimes there are projects where we only need 1. So be it. There are situations where you need only 1 cable or 2 or 3 or 4. And how it's coded, it's like this. Now, these codes may change from country to another, state to another, depends on the main supplier in that area. And that's basically, so you don't need to worry about it, just understand what we're talking about here. We're talking about the number of strands and the braking force it can take. And the 12.7 is coded by S5. And the 15.2 strands is coded by S6. This is just coming from the supplier, which helps the construction engineer to make the right order as well. Galvanized ducts. Sometimes our ducts may be used in external areas like bridges, and to make sure maybe they're going to be moisture. Like if you're designing a concrete slab for a road or a bridge and it needs to be PT'd, then there is an option where you use galvanized ducts, which are more expensive, and they're giving you all the sizes here. There are sometimes polyethylene, which is cheaper. You don't need to be galvanized, and you can actually have the plastic-based or aluminum-based ducts, which we use them for internal slabs. And they also specify the dimensions and the spaces for them. All right, so tendons supports. Here they're giving you some kind of recommendations about how to space the ducts. The ducts, again, if you're following, these are the ducts. Usually these are the ducts. Or in the other last week's lecture, did I close it? No, I had it open. Just had it open. Yeah, these are the ducts I'm talking about. Those guys, they are the ducts. So they're giving you some specifications here, which helps the engineer to design them, because usually what you're going to be following are the structural drawings. The engineers who did the structural drawings, they're going to be following these recommendations we're sharing with you. Right now, in your assignment 2, we're asking you to nominate these kind of sizes. You're not designing it, you're just nominating. So make sure you kind of consider these kind of arrangements we're talking. Okay, my document closed. Let me open it again. So the details I was showing to you on this slide here, you may use them to nominate the spacing of your cables in your band beam or in your slabs as well. And I would suggest you for the slabs, just go with the maximum available, which is 1 meter here. Curving the slab. Yeah, this is basically just to give you an idea when the engineers will be designing the curving, how the cables are going up and down. The engineers will be specify them for you, and they use basically quite of detailed equations to do that, or softwares to do that, which you don't need to worry about, given you are not studying design, you're studying the construction. So in the end of the day, basically, you don't need to specify curvature. You are specifying the depth of the cable, which we discussed, and we're going to talk more about during the workshop. the depth of the cable, how it's going to be going down and up. And please make sure in your assignment, don't choose a number where it's actually telling me the cable or the duct is flying above the slab, because it's wrong. Okay. So make sure you apply this kind of arrangement as required for your assessment. Losses, yeah, I will talk to you now about losses, as I said. So here we're talking about percentage for the overall losses that the cable will experience over its entire life, or like 30 years or whatever. We, like engineers design, I know the buildings can stay up to 100 years, but usually we design for a particular age, 50 years, 40 years. It depends on the project importance. So just an idea, the edge stressing, internal pocket stressing. So you see the differences I was talking to you about before? So that was the pan. When we had the life load from the top of the slab, we will have 5% stresses. So there's a 2% difference, which means more steel and more cables to add in your slab. Edge stressing, when your life end is at the edge or the side of the slab. Internal pocket, where we have to put the pan on top of the slab, you already costed the project 2% losses from the stresses, right? That's for your information. So that was frictional losses at the anchorage due to curvature. Basically, the reasoning, when you have a life end, we have, just to clarify this, maybe if people, again, the orange shape here is when we got the stressing from the side, and the blue case here when we got the stressing from the top. So the curvature here is higher. That's what we're saying here. Friction losses in the anchorage due to curvature. The curvature here is steeper. That's why it's going to cost more losses. More losses means more steel required to achieve the required strength, right? So here it is the 5% losses, and here it's the 3% losses. Now, another type of losses, frictional losses along the tendon, which I was always talking to you about. This is frictional losses about along the tendon. If I have like kind of a profile which can help me to talk about this, yeah, here we go. This is a good profile. So as the cable goes up and down, there is actually, during the tensioning process, you know, when the contractors are pulling the cable, they're going to be pulling this cable by, as we said, 300 millimeters for that example I was calculating. While he's pulling, he's not only applying force on the cable, he's actually resisting the friction as well. So that force he's generating to react on the concrete, it's not only to lift up the slab, as we said. While we're doing the cables up and down, it's going to be lifting. So here we're going to have a force pushing this way and a force pushing this way that will end up lifting the concrete up. This is the main reason of using PT. Now, because there is a friction between the cables or the strands and the conduit, we have to resist this force as well. And that's why we consider it as losses, right? So let me go back to where I stopped. Here. So that's what we're talking about, and this got some decent figures of losses. Okay. And yeah, to calculate those losses, the frictional losses, it depends on the quality of the conduct of the conduit, sorry, or the ducts we're using. If we're using the conventional steel ducts, is 0.2. If we're using the poly-based ducts, it can be 0.13. So really, this can happen. Ideally, which is cheaper option, we go with the polyethylene, which the friction is even smaller. The friction coefficient is even smaller. But as we said, sometimes if we have to use galvanized steel to help with the galvanized steel will be used for external concrete slabs, for roads, bridges, exposed concrete floors. We have to go with this figure here, which means more friction. The third type they are talking about here, it is the wedge draw in, which is that little wedges I've talked to you about already here. These kind of wedges here, this one. As I said, by the time they cut the cable will slip by 6 mil. This 6 mils means losses, which we cannot avoid. That's approximately what we're talking about here. Okay. So before I show you that chart, which will let you imagine and feel the level of losses, these slides, I think, yeah, they're talking about here the reinforcement. As I said to you, with post-tensioning, there is always special cage of reinforcement at the live end and dead end. To let you know, usually these cages are specified by the supplier, like VSL. They will tell you, if you're going to use our cables will maximum take this figure, and if it's taking this figure, this level of steel anchors are enough. So that's a kind of a standard approach, and you're going to you will be showing me these kind of details on your drawings, and even in the practical drawings I'm sharing with you. Let me go to them quickly. You know, let me go to the engineering drawings I shared with you last week, and you will see such. They're coming here. I kind of shared with you. Here we go. It's kind of specified here. We have R10 wires, spiral. Basically, the engineers have taken such details from the suppliers, just to let you know. And they are kind of standard because they are designed not for specifically for the project. They are designed for the maximum what the cable can take. Unless you have very special project, where, as I said, you may have a very deep beam, like those transfer beams I showed you in the last week, then they will need a special design. But this is beyond the scope of this subject. You just need to understand, for post-tensioning, we have reinforcement, cages of reinforcement placed at the ends. Unlike pre-stressing, that's not happening because there is no concentrated force at the end. No concentrated force at the end. Right. Let me now go back to our notes to progress. So the details, the spaces, the dimensions of all what we're having here are provided again by the suppliers, which you can see. Anti-burst reinforcement, they call this reinforcement anti-burst because of the concentrated force. Large concentration of stresses are at the ends for the post-tension cables. Again, we're talking about post-tension systems. We have those large concentration of stresses which we want to resist. We want to make sure the concrete will not get crushed, right? And we have to put those anchors. Concrete must be adequately compacted. Usually, as you vibrate the concreters, when they place the concrete, they need to have adequate workability, adequate plastic super plasticizers compacted very well to make sure you don't have spalling, you don't have gaps, you don't have voids, because you will have very early cracks there, then something will go wrong. Yes, so the anti-burst reinforcement, they are there to resist those high stresses, which they will be placing after 24 hours. And there are two types of anti-burst reinforcement, the helical type and the ligature. So the helical, they are sometimes something similar to what I just showed you here. Yeah, they come like a spring around the cable, and that's what they call the helical type, which is, it's basically one cable in a spiral shape, But sometimes they can be custom made on site, where they use ligatures. And I think it's not an option we provided here because for slabs, we typically use the spiral helical option. So let's see, let's go back to the notes and see the two types. I trust they are, yeah, here we go. This one is talking about the spiral option, which they're gonna come from the suppliers. Now, they also, all the dimensions and the coding, they're telling you for this type of coding, that was the 12.7 S5, you can use this dimension. So dimensions are important to help contractors to know what they have to allow for in terms of dimensions and all the spacing around it. Okay, they also got, this is from the supplier, some jacking, which is the force that we need to apply. So what they're saying, if you're going to be using this detail, you have to make sure you're going to be stressing the end by this much of MPa, right? And the bar should be reaching these figures. So this is the, we're not talking here about the cable, we're talking about the steel type of the spiral, right? So that's, which is not really high. This is even cheaper than what I was saying to you. The normal steel bars, like the N16s, the slab reinforcement, they go to 500 MPa. This one, this is the round bar, they are cheaper. They go less carbon in their material, so they are cheaper because they want to flex them in this shape. So they don't want to have they don't want to work with very hard steel. Okay, so this is the ligature type. So they use basically something similar to the shear bars, the stirrups we use for shear reinforcement. They are ligatures. They're going to do the same job. They're going to prevent the burst. They're going to prevent the crushing of concrete at the end. It's really up to the construction site what they want to use. Sometimes if you have very deep sections and the spiral are not available to count for such area, they will end up using ligatures, which is an option. But just to let you, as a construction subject, this is all specified by the engineers. Point here is to know their importance, why they're there, and you need to allow for them during construction. Okay. Some more detailing for the ligature type, anti-burst reinforcement for the ligature type. Remember, they are placed, these are the ligatures. This is the plan view, that's the life end. And these are the 4 ligatures, 1, 2, 3, 4, and these ones gonna still be required. They're gonna go across the anchor to help with the system. So it's not only about having the ligatures along the anchor or the end, they also need to have those reinforcement to distribute the stresses over a longer area and prevent the anchors. If we have a band beam or an edge beam, there are further detailing to be considered, which is, again, we have those U-bars to help with the whole anchor and the stresses if you got an edge beam like this. Now, again, this is just something specified on the drawings, which it may be applicable for your project or not, right? And I trust in your project. No, actually, you at the ends, your pile's going to be built before. So you have the pile caps and you have your slabs. The PT is actually in your slabs, not in the pile cap. So you simply got slabs ending at the pile cap. That's where you're going to have your life ends or dead ends. So this won't be applicable for your first floor slab. Right, this one just explaining to you how the forces are resisted when you will be imposing compression here. After you cut your tension bars, you're going to be imposing compression. The force will be distributed along the entire area, which is resisted by those ligatures as well as longitudinal bars across the end as well, right, to prevent the horizontal crack development. And as I said, whether you use the ligature or the helical type, they're going to do the same job. just a similar manner. It's not really different. It just depends about your preference, which one you want to do them on site or you want to order them from the suppliers. It's really up to you, right? And just understand we are here preventing two types of cracks, the vertical ones and the horizontal ones. The vertical ones will be resisted by the ligatures. The horizontal ones will be resisted by those longitudinal bars. Now, I think so far we kind of talked about, I've talked to you about the first slide I was talking about. Spent about an hour there talking about the detailing the PT system on your drawings and what you need to know from those details and apply for construction such systems. Then we talked about the dead end and live ends and how they are coded by the suppliers. We talked about the components of the live ends. We talked about when we talked about the live ends, there were several components, like you need to know where is the duct, you need to know where is the wedges, you need to know why we're using that tube, the grouted tube. Make sure you understand all those points. Then when we've gone through all those dead end and live end details, I showed you images and details. And also this document will give you more about the dead end types. We have two famous dead end types, the onion and the plate dead end, live end, same, we talked about it. Then at the very end, we talked about so far the reinforcement, the anti-burst reinforcement we need to put at the dead end and live end. They can be as simple as spirals supplied by the contractors or the suppliers who provide you with the cables, or they can be custom made as ligatures, right? And now we reached a point where we're just talking about the tools or equipments used to stress those cables, right? And it can be as small as this. Same thing, the supplier, who's, for example, can be the BSL, they will provide you, which is, I will share this with you as well, they will provide you with the, here we go, I think it's sitting somewhere. Is it here? No, this, I think here we go to very special, yeah, this is very heavy duty projects where they use PT as well, but I just want to show you the, yeah, here we go, the tool, this one. So slab post tensioning, it's really a very quite small jack. And they're going to be, they use this tool to stress each strand, right? Something like what you see here. Now, the key thing I want you to know is the dimension. That's why we need to make sure this helps the contractors and construction engineers to know whether they have the space to do so, right? So they need to make sure this image is very important. It just tells in case if you want to stress the cable from the side of the slab or the beam, you need to have this dimension or space at the stressing end. The jack itself will require about 400 millimeters. You need 600 behind. I know this is not to scale because 600 is longer than 400. And just because you need a person to stand in the back and do it. Overall, you need 1 meter. That's really important. If you're going to need to think about, if you had no option, you need to make it from the side, because architecturally, the architect says this is a warehouse. They need a very special fancy finish for the concrete. I don't want any pockets, any patching to be seen from the top. Then for that project, you have to tension from the side. And let's assume you do have the space, no boundary lines. Then you have to allow for a scaffold that will be minimum 1 meter wide, right? You have to have a scaffold that will be minimum 1 meter wide to allow for a person to stand back here and stress your cable. So this is importance of such information is to find out what space you need to get your cables stressed, right? It's not only there for other reason, but it's just to help you to process the construction. Yeah, because this kind of arrangement, if they are missed, they can cost a lot. Now, there is sometimes the jacks, if the cables, I think I've seen a case where you have much bigger jacks. I just don't know where is that case. There is a cases of situations where you have a big machine to do your stressing, something like this. But this is actually for bridges. No, there is also like a deep beams, which, no, it's not here. So maybe they did not cover it in this document. But sometimes we, in kind of deep band beams, if we need to use more than the 15 cables, we have to have a larger. I think, no, these are heavy duty. Yeah, I just want to, here we go, this one. Yeah, you see this one here? This is kind of used for cables. Let me see the size of cables they will help us with. They are not the normal ones. So there are cables which actually goes bigger. Say 19, we start getting to 19 cable size, 42, 52. So they kind of much larger. We won't have this in our assignment, or it's not within this kind of the scope of the subject, but I just want you to know those jack details, the stressing jack details, they may require even much bigger room. So if you see B here, B is still 1 meter, so no, it's not. Yeah, I can say like it can go up to 2 meters, depends on the size, 2.4, because really this kind of machine, they are tensioning machines and equipments, and they will require a bigger room in case your cable is not the small ones, the standard, the S5 or S6, which is the 12.7 or 15 diameter. If we go bigger, we can get to 22 or 30. You need to allow for a bigger room, and this kind of things need to be thought about from day one, right? As soon as you see the drawings, you have to pick those issues, because if you didn't know about them and you sign a contract to do the job, then that's it. You have to find a way to do it. It's going to be difficult to go and ask the engineers. I think this is just the image I was trying to show you. Yeah, you can see things can be as large as this equipment. So you need a bigger space. Sometimes the construction process sometimes is missed, which is a big pain. It's easy for the designer to throw some cables on the drawings, but you need to think about its implementation. Is it feasible or not? Okay, so basically these slides is talking to you about the spaces required around the tools we use to stress our cables. In this subject, we basically talking to you about those small scale tools. Whether from, this is when we have a pan case, this is when we have a side edge case, and here we do have just the profiles we talked about last week. PT design, we're talking about PT design here, which I'm taking you through all those detailings during the workshop, and we will be talking more about it this week. Right, so so far we have covered the details. Just back to our notes. Is there any question about what I mentioned there? Go back to the notes, and maybe I will leave those images and some major notes about the PT to be covered during the workshop. So now it's about 9:52. We can talk about this because this is going to be parallel to what we're doing. Then after I go through these notes, I will be, so we have just maybe about 10 slides. 10, 15 slides to go through. Basically, they're just going through some construction process, which is to do with timing we covered already. And some of those notes are related to your assignment, so I will be talking about it. Those tables just shows you basically the costing, the cost differences between RC and PT. So it can show you in some cases you can be saving. That's for 2 6-meter spans, but if you have large projects, multi-floors, this will add and add and add more. So we're just showing you roughly what the cost is, but remember this was few. I think now the prices have changed, but it's changed for both. The prices have increased, whether for RC or for PT, but both of them are increased, not one of them. So the difference should stay same. Yeah, we just want to show you how prices, how PT can be economically more viable to use in projects. Because if you're going to go with RC, the thickness of the slab is actually thicker, but with PT, the thickness of the concrete can be thinner. Yeah, and then although the cables, in terms of steel, going to be a bit more expensive. This is just another example, which shows you, again, if you got 8-meter spans, you can also save about 3,000, 3 grams between. So just an economical study, quick economical study for you to see the key advantages from using the PT. This is the cable. I think I will just end with this cable, and next week I will start from these general notes. Sorry, not next week. During the workshop, I'll start from here, just maybe for half an hour. I go through the slides, and then the rest of the workshop, really, I will be asking you guys, asking the teams. Is there a team who wants to show me what they did? During the workshop, I will finish up those 10, 15 slides and see how they are related to your assignment. Maybe this was the one I was talking about in terms of losses. I'll talk about this in a minute. You see, up to this line, right, we're showing that's the transfer of pre-stressing. We're transferring the stress from the cable to the gray concrete. That's why we call it transfer of stresses. It means the process it will take the contractors to transfer the stresses from the cables, which they developed by the jacks, to the gray concrete. They're going to have this drop, and this again sharp drop, then this another steep drop. So all those sudden drops. This one here can be, I think you can read it from here, relaxation before. It's actually this one here. So this one, you see this drop? If you read it carefully there, it is due to the what? The gripping, the slip, those 6 millimeters or 4 or whatever you're going to be using. So you see this sharp slip happens due to the draw. Then you're going to have this relaxation in the tendon. Then you're going to have another shortening due to elastic shortening, which is related as well to the early shrinkage, which is happening. So it's really strong drip because the slab going to get shortened, or the beam going to get shortened because it's still fresh. Now, over time, over like many years, 20, 30 years, the steel and the shrinkage and the creep will also cost more losses. But in the end of the day, to let you know, this is what the engineer going to be designing for. The engineers will be designing for this level. So everything is counted for. That's why in PT, you have to be very careful not to over stress. Because if you over stress, you may actually break the slab. You may lift it up more than required. Because the engineer have already allowed for losses to happen, so they have to happen. If they did not happen, then your slab may be overloaded permanently. Anyway, we'll take you slowly through over maybe, as I said, half an hour. We'll talk about those losses. Then we have some images to share with you about construction and just some generic information about PT. Then I can close up the notes and will be ready during the workshop for about 1 hour plus 1 hour and a half to talk about your work on assignment to project. Okay, any questions for me?